Hi everyone, my name is Bastien Sadoul. I'm an associate professor at l'Institut Agro, and today I will speak about Holothurians from the ecology to pilot studies that we run in the Integrate program. So the model will be in 5 different points. The first, the biology and ecology of European Atlantic Holothurians, the status, management and regulations of the fisheries, how to reproduce, raise European Holothurians, the different Holothuria production systems that we are able to run as partners of the Integrate program, and the pilot studies that we run in the Integrate project. So first, the biology and ecology of the European Atlantic Holothurians. So all the Holothurians are part of the class Holothuroidae. This class is within the phylum Echinodermata, so all the Holothurians are echinoderms, and they are all animals. Within the class, we have 7 different orders and a lot of species. We count so far 1,700 species all around the world. Within Europe, and most importantly within the European Atlantic coast, the area of the Integrate project, we have 5 different species that were previously investigated for their aquaculture potential. We have Holothuria foscali, Holothuria mamata, Holothuria sanctori, Holothuria tubulosa, and Holothuria arginensis. On the European Atlantic coast, there is multiple other less described species, but today I will speak mostly about those 5 species that I just talked about. They are all living in shallow waters from 1 meter to 100 meter, and they are distributed over the Atlantic coast, European Atlantic coast, with the Holothuria foscali going the most up north, Holothuria arginensis in the middle, going down to the south of the Europe, and Holothuria sanctori going down to the Canaria. They are also benthic detritivorous, supposedly, we hope. So it means that they feed on the detritus on the bottom of the sea. In terms of biology, they are overall having a cylindric body. They have a very thick body wall for some of them. They have inside the body wall calcareous ossicles. They have a mouth here surrounded by tentacles, and they have tube feet called also podia for the adhesion and locomotion on the sea. They have an annual and synchronous reproduction. You have it here for Holothuria foscali, Holothuria arginensis, and Holothuria sanctori. So for foscali, you can see it very well here. You have the gonadosomatic index, which is very high until March, and certainly the gonadosomatic index of individuals caught in the wild are dropping very quickly and going down to almost 0 in April, meaning that reproduction is probably being very synchronous and only happening once in the year at the end of winter. You can see it here for Holothuria arginensis in the middle. You can see that the gonad index is at its maximum in June, July, meaning that reproduction is probably happening at the middle of summer. And you will see here on the right for Holothuria sanctori, you have a very similar trend than the one you can see for arginensis. All these species, they spawn in the water column. You can see it here on the left for the males and on the right for the females. And they have 2 different life stages. A first life stage, which is pelagic, meaning that the eggs and the first stages of the life of the Holothuria is within the water column. So you can see it here, the different life stages. So you have first a larval life stage, And then a second stage, which is benthic, so the larvae is transforming, is having a metamorphose, transforming the larvae into a small juvenile that we call pentactula, and the pentactula is then becoming growing, and so this is a juvenile growing or becoming then an adult and a mature adult, which will then be able to reproduce. What about the sea cucumber status, management, and regulation? So first, I wanted to show you that there is a huge increase in the catches. These are data for fisheries coming from the software FishStatJ. And so there is a very strong increase in the catches of Holothurians since roughly the 2000 years. This is mostly due to a high price of sea cucumbers. Half of the catches are not reported. This is often because they are not simply legal. The fishing is mostly unregulated in most of the areas, leading to more than 70% of tropical stocks being fully exploited or even overexploited or even depleted. The current status fishery management, so the overfishing in the Indo-Pacific has resulted in catch of new species now in the Mediterranean Sea. So the stocks in the Mediterranean Sea are decreasing, and now fishing is also running on the northeastern Atlantic coast. The main countries in Europe exploiting these resources are Turkey, Spain, Greece, Italy, and Portugal. In Spain, the fisheries mostly focus on Parasticopus regalis, leading to an overexploitation of the stock, as I mentioned earlier. And so other species are now also targeted by the fishery sector in Spain and Portugal. And now we have more than 10 companies that export sea cucumbers to China. And the species that are exported are the one that I spoke about earlier. What about their current status? So the UICN doesn't have enough data to have a clear category for these species, and so because of that, there is also no clear fishery management plan. What about the regulations and the protection of these species in terms of fisheries at the international? So there will be many different regulations that are in place in different countries. So you have some referenced here. And also in the Europe. So in Europe, fish regulations are very scarce. There is some legislation to control Holothuria foscali in Galicia, but there is no other control in other regions. In Portugal, there is some legislation a bit on Holothuria foscali and Parasticopus regalis, and there is some areas that are totally forbidden for fishing of Holothurians. This is the case in Ria Formosa. How to reproduce and raise Holothurians now. So this is the example of how we do it here at l'Institut Agro on the species Holothuria foscali. So we first stock broodstock from the wild. We run some biopsies to evaluate the maturity of the individuals, and we do this using microscopic observations of the gametes. So here you have, for example, two photographs of the oocytes from the females and the sperm from the males on the right. Then we are able to induce reproduction, and to do that we use at l'Institut Agro tanks of 24 liters. We put 3 individuals per tank, we have a pretty good renewal of the water, and we feed them every day with a mix of commercial pellets coming from the shrimp sector and algae. And so we feed them with that, and we increase the water temperature, and this is what makes them come into reproduction. And so after 3 and 5 days, after the increase of the water temperature, we have gamete emission, and we recover the oocytes by siphoning the oocytes, and we incubate them. And usually we have about 85% of fertilization, which is very good. And then we can also run artificial reproduction. To do that, we extract the gametes, so we kill the embryos, extract the gametes, and we fecundate the gametes with the oocytes with the spermatozoids, and we incubate. And usually we have much lower fertilization rates, between 25 to 75%. Here is briefly the protocol. Then we incubate the freshly fertilized eggs into different tanks. We tried plenty of different tanks. We usually found that the best incubation density is about 1,200 embryos per square centimeters. We have a 100% water renewal per day, and we incubate them for Holothuria foscalia at 15 degrees. We don't feed them during 72 hours. There is then the larval rearing that we did try in different tanks, but the one that were the best were the conic tanks, such as this one on the picture. We use medium to large tank size, 40 to 125 liters. We put 1,000 individuals per liter, and we have a 200% water renewal per day that we, of course, filtered and sterilized before putting in the tank. We incubate at the same temperature, between 15 to 16 degrees, and we feed them with the phytoplankton, and these are diatoms and dinoflagellates, and this runs during 25 days. Then, as I said earlier, there is a metamorphosis, so transforming the larvae into juveniles, the juveniles becoming benthic, and this we run this in 24 liters rectangular tanks with vertical plates where you have the diatoms, benthic diatoms. You have we put 1,000 individuals per liter, and we renew a lot the water, around 400% of water renewal per day, and the individuals are incubated at a bit higher temperature, between 16 to 18 degrees, and this runs during 27 days. So overall, the success of this type of rearing, so as I said earlier, we have 95% of fertilization, and we are able to get at the auricularia stage with the success survival of around 25 to 35%. We lose some during the metamorphosis stage, and once they are juveniles, they are very easier to grow, and we have much less mortalities. And so overall, we estimate, because we didn't finish the entire cycle, but we estimate that we will have around 11% of survival. So just to compare, this is pretty good, since for oysters it's 25%, and the oyster production is very well known and very well studied for now decades. So having a 11% survival is already good. Here is the process for Holothuria sanctori. Holothuria sanctori. So there is also the possibility to induce the reproduction. So what they do in the University of Las Palmas, they do a mechanical shock to induce the reproduction, which will lead to an explosion of the gametes after a few hours, and this allows to get very good fertilization also with mate. Here, briefly, the development from the embryo to the larval stages. You have very nice pictures of the development of Holothuria sanctori. This is performed in tanks of 180 liters with a stocking density of 300 larvae per liters, 200% water renewal per day. This time the temperature is much higher, 21 degrees, and the individuals are fed with the phytoplankton, diatoms, and nanochloropsis. This lasts during 20 days. This was about the rearing. Now the pilot studies in the Integrate project. We were able to run during the Integrate project 3 different prototypes, pilot studies, running using Holothurians. So the first one was performed at the University of Las Palmas in the Gran Canaria using Holothuria sanctori that were grown within their facilities and reared within their facilities. And the Holothurian sanctori were tested underneath abalones in a very controlled environment, so in tanks at the university. So what was done within the integrated program, abalones were put in a compartment at a density of 50 individuals per square meters, and they were in a compartment that allowed the feces to go down to the bottom of the tank, which was available for the sea cucumbers that were stocked at a density of 2.5 individuals per square meters. And the whole tank was 300 liters, and the experiment lasted 2 months. So here a bit of the results. Survival was excellent, and what is very important is to show that Holothuria sanctori was able to grow very fast using the abalones feces. So they gain more than 80% of the weight within the 2 months of the experiment, which is very good. Here's what was done in a bit less controlled environment in ponds by City Aqua in Spain, south of Spain. So this was using these pilot studies used Holothuria archinensis in ponds, and the Holothurians were put with 2 different species, fed species, Sparis orata, the sea bream, and they were put with the Japanese oysters, Magellana gigas. And so all these 3 species were put in the ponds for 2 months as well, and the results are still to come, so stay tuned. And finally, the third pilot studies was running Holothuria foscali underneath flat oysters in this time a very open environment, because we put them in the sea, and this was performed in Brittany by l'Institut Agro. So here you have the structure of what was run in the pilot studies. You have the structure with flat oysters, which are in oyster bags, and underneath you have Holothuria foscali, which are stocked underneath in also oyster bags, and we used this time flat oysters rather than Japanese oysters. And the experiment lasted 15 months this time, and we started with the Holothurians that were 5 grams, and we ended up with intervals that were 20 times bigger. So within the 15 months we had excellent survival, 98% of survival, which is great, especially during 15 months. And we had, as I said before, very good, excellent growth with the Holothurians underneath the flat oysters. And now the next step within the integrate program is to try to show if they actually grew from the waste of the flat oysters, and we use isotope analysis and fatty acid analysis to try to demonstrate that. So to conclude this module, Holothurians have very important commercial value, which led to overfishing in many countries. Few species are now domesticated in Europe, and we are able to finalize the whole life cycle of only 2 to 3 species. We were able to run pilot studies, and these pilot studies within the Integrate program showed extremely good growing potential of Holothurians in IMTA systems. And eventually we will be able to show that Holothurians are able to reduce the particulate waste from aquaculture production. This was done at the University of Las Palmas. They showed that the Holothurians were able to grow using the feces. So it means that they are able to extract particulate matter from the aquaculture production. We still need to demonstrate that for Holothuria foscari at Institute, I hope. Thank you very much for your attention, and you have all the list of the partners of the Integrate program here. Thank you. Bye.